all the time. For example, changing of coal when it is burned to produce heat, changing of milk into curd, and rusting of iron when exposed to moisture. All these changes are a result of chemical reactions. These chemical changes can be represented through chemical equations. In this lesson, you will learn about writing and balancing chemical equations. At the end of this lesson, you will be able to define a chemical reaction, explain the symbolic representation of a chemical reaction, identify the components in a chemical reaction, explain how to write a chemical reaction, and balance a chemical reaction. Let us see what a chemical reaction is through an experiment. We begin with some zinc granules in a conical flask. These granules are blue-gray in color. Fit a 2-holed rubber cork on this flask. Then we fit a thermometer into one hole of the cork and a thistle funnel into the other hole. Next, pour 5 ml of dilute sulfuric acid into the conical flask through the thistle funnel. The color of the zinc granules changes from blue-gray to white. Some gas bubbles are also released from the solution. This is because zinc reacts with sulfuric acid to form zinc sulfate and hydrogen gas. Zinc sulfate is white in color. The thermometer shows an increase in the temperature of the solution. Therefore, as you saw in this experiment, the color of zinc changed during the reaction. That is, there was a change in physical properties. The reaction also resulted in the evolution of a gas. That is, the form of the reactant changed. Zinc reacted with sulfuric acid to form zinc sulfate, a salt. Thus, the composition of the reactants changed. Hence, we can say that a chemical reaction involves a change in the physical and chemical properties, the composition and the physical state of a substance, whether an element or a compound. A chemical reaction is typically expressed in terms of a chemical equation. A chemical equation indicates the components in a reaction, the physical state of each reactant, and the products of a reaction. Thus, a chemical equation is a symbolic representation of the reactants and the products, using their chemical formulae. For example, zinc reacts with dilute sulfuric acid to form zinc sulfate and hydrogen gas. This is represented in the form of an equation, as shown here. Solid zinc reacts with dilute sulfuric acid to form an aqueous solution of zinc sulfate and hydrogen gas. A chemical equation is made up of the following components. The reacting substances, known as reactants, are on the left-hand side. For example, in the equation you just saw, zinc and dilute sulfuric acid are the reactants. Therefore, they are on the left in the equation. The resulting substances, known as products, are on the right-hand side. For example, in the equation, zinc sulfate and hydrogen gas are the products. Hence, they are on the right. An arrow separates the reactants and the products, and also indicates the direction of the reaction. Thus, in the reaction you saw, the arrow indicates that zinc and sulfuric acid react to form zinc sulfate and hydrogen. Let's take another example that involves two substances. In the burning of coal, carbon reacts with oxygen to form carbon dioxide. In this reaction, carbon and oxygen are the reactants and carbon dioxide is the product. The chemical equation for this reaction is as shown. Solid carbon reacts with oxygen gas to form carbon dioxide gas. In chemical equations, you denote a solid with S, a liquid with L, a gas with G, an aqueous solution as AQ, a gas produced with an arrow pointing upward, precipitate formed with an arrow pointing downward. The reactants and products are separated with an arrow, which points in the direction of the reaction. Let us consider the reaction of iron with steam. Solid iron reacts with steam to form solid iron oxide and hydrogen gas. This reaction is represented as shown. A symbolic representation of a chemical reaction is the first step in writing a chemical equation. The next step is to ensure that the equation is balanced, considering the law of conservation of mass. The law of conservation of mass states that the total mass of the reactants and the products should be equal. This means the number of atoms of an element on the reactant side should be the same as the number of its atoms on the product side. All chemical equations must adhere to the law of conservation of mass. Therefore, all chemical equations need to be balanced. The process of balancing a chemical equation involves 4 steps. Determining the reactants and products in a reaction. Counting the number of atoms of each on both sides. Selecting the elements that occur for the least number of times in the equation. Balancing typically starts with such elements where the number of atoms is not equal on both sides. Changing the coefficient of the molecules of reactants or products as required. You should continue balancing the atoms in this manner till you have covered all the elements in the equation. In the end, do a final check to confirm that the number of atoms on the reactant side and the product side have been properly balanced. Here is a word of caution. When you balance equations, use coefficients only on the left of the symbols of elements and compounds. Never change the formula of a compound or an element to balance an equation. To understand how an equation is balanced, let's refer back to the reaction of hydrogen with oxygen to form a molecule of water. We need to balance the equation for this reaction according to the law of conservation of mass. The first step is to determine the reactants and the products in the equation. Here, hydrogen and oxygen atoms are the reactants. Therefore, they are written on the left-hand side. The water molecule is the product, and hence it is written on the right-hand side of the equation. In the second step, you need to count the number of atoms of each type. You'll notice that hydrogen has 2 atoms on the reactant side and 2 atoms on the product side. But oxygen has 2 atoms on the reactant side and only 1 atom on the product side. So there is 1 oxygen atom less on the product side. According to the law of conservation of mass, the number of atoms on the reactants and product side should be the same. In step 3, you need to select the element that occurs in the minimum number of places in the equation. You can see that there are 2 hydrogen atoms on each side, while there are 2 oxygen atoms on the left-hand side and only 1 on the right-hand side of the equation. Hence, oxygen has to be balanced first. Finally, in step 4, you change the coefficient of the molecules of the reactants or the products. To do this, you need to first select the oxygen atom and balance it by placing the coefficient 2 before the product H2O. Now there are 2 oxygen atoms on the reactant side and 2 on the product side. However, placing the coefficient 2 before H2O gives 2 hydrogen atoms on the reactant side and 4 hydrogen atoms on the product side. Thus, there is an imbalance in the number of hydrogen atoms. To balance the hydrogen atoms, place the coefficient 2 on the left hand of hydrogen on the reactant side. Now, let's take a look at the final equation. The atoms of each element on the left and on the right hand side of the equation are now balanced as per the law of conservation of mass. According to the final balanced equation, 2 molecules of hydrogen react with 1 molecule of oxygen to form 2 molecules of water. Let's practice further on balancing equations with another example. This equation deals with the combustion of ethyl alcohol. Again, the first step is to identify the reactants and the products. Here, ethyl alcohol and oxygen are the reactants, and they are written on the left-hand side of the equation. The products on the right-hand side are carbon dioxide and water. Step 2 is to check the number of atoms of each type on either side. Here we have 2 carbon atoms on the left-hand side, but only 1 on the right-hand side. 6 hydrogen atoms on the left-hand side, but only 2 on the right-hand side. 3 oxygen atoms on the left-hand side, as well as on the right-hand side. Let us begin balancing the equation by selecting carbon. There are 2 atoms of carbon on the reactant side, but only 1 atom on the product side. So to balance this, add the coefficient 2 before carbon dioxide on the right-hand side. Now, let's consider the next element, hydrogen. There are 6 atoms of hydrogen on the reactant side and 2 atoms on the product side. To balance this, you need to place the coefficient 3 before H2O on the product side. Now, as you can see, hydrogen has been balanced. The next element in the equation is oxygen. There are 7 oxygen atoms on the product side, but only 3 atoms on the reactant side. To balance the equation, place the coefficient 3 before oxygen on the left-hand side. In the end, do a final check to confirm that the number of atoms on the reactants and the product side is properly balanced. Here is what you get as the final equation. Ethyl alcohol reacts with 3 molecules of oxygen to give 2 molecules of carbon dioxide and 3 molecules of water. Actions. Have you ever wondered why silver gets tarnished? Crackers contain chemical substances like aluminium, barium, calcium, etc. that burn in oxygen to impart a silvery white sparkling effect with green and orange colors. Thus, elements get oxidized when you burn crackers. Similarly, silver reacts with hydrogen sulfide in air and forms black silver sulfide. Thus, silver combines with sulfur in this reaction. All chemical reactions can be classified based on the different ways in which elements react with each other. In this lesson, you will learn how to classify reactions. At the end of this lesson, you will be able to classify chemical reactions, describe the characteristics of each type of chemical reaction, identify exothermic and endothermic reactions. Chemical reactions vary depending on the chemicals involved in the reaction as well as the environment of the reaction. For example, the rusting of an iron nail is an oxidation reaction. On the other hand, the digestion of food in our body is a decomposition reaction where the complex food substances are broken down into simpler substances like glucose that give energy. Chemical reactions can be classified into following types: combination reactions, decomposition reactions, single displacement reactions, acid-base or neutralization reactions, double displacement reactions, combustion reactions, and oxidation, reduction, or redox reactions. Let us begin with combination reactions. A combination reaction is one in which 2 or more reactants combine to form a single product. The reactants may be elements or compounds. The general form of the reaction is A combines with B to form a single substance, C. For example, coal burns in oxygen to form carbon dioxide. In this reaction, the two elements, namely carbon and oxygen, combine to form a single product, carbon dioxide. Let's take another example of calcium oxide reacting with water to form slaked lime or calcium hydroxide. In this reaction, the two compounds, namely calcium oxide and water, combine to form a single product called slaked lime. You must remember that a combination reaction has many reactants but only one product. Decomposition reactions are the opposite of combination reactions. Decomposition reactions are those in which a substance splits into two or more simpler substances. The general form of a decomposition reaction is AB decomposes to give A and B. Decomposition reactions use heat, electricity, or light energy. Decomposition through the action of heat on a substance is called thermal decomposition. For example, calcium carbonate on thermal decomposition gives calcium oxide or quicklime and carbon dioxide. Decomposition of a substance by passing a current through it is called electrolysis. For example, when electric current is passed through acidified water, it decomposes to give hydrogen gas and oxygen gas. Finally, the decomposition reaction resulting from action of light energy is called photolysis. For example, when silver chloride is exposed to light, it decomposes to form silver metal and chlorine gas. Remember that a decomposition reaction always has one reactant and many products. Now let us look at the displacement reaction, beginning with the single displacement reactions. A single displacement reaction is a reaction in which an element reacts with a compound to substitute or displace an element in that compound. The result is a new compound. The general form of the reaction is written as C displaces A in AB to form CB and A. Generally, in a single displacement reaction, a less active metal is displaced by a more active metal. For example, in the reaction of magnesium with copper chloride, magnesium takes the place of copper to form magnesium chloride. It is important to note that in a single displacement reaction, one of the reactants is always an element. For instance, let's consider another reaction where magnesium sulfate reacts with copper chloride to form magnesium chloride and copper sulfate. Even though this reaction seems similar to the earlier example, it is not a single displacement reaction because both the reactants are compounds that exchange ions. An acid-base reaction is a special kind of displacement reaction between an acid and a base. Most acids have the general formula HA, where A is an anion, while most bases have the form BOH, where B is a cation. In an acid-base reaction, the hydrogen ions of an acid react with the hydroxide ions of a base to form water. Therefore, in the general form of an acid-base equation, HA, an acid reacts with BOH, a base, to produce water and a salt, Ba. An example of an acid-base reaction is the reaction between hydrochloric acid and sodium hydroxide. In this reaction, the chloride ions in hydrochloric acid and the sodium ions in sodium hydroxide react to produce sodium chloride or common salt and water. Another example of an acid-base reaction is the reaction of sulfuric acid with sodium hydroxide. In this reaction, the sulfate ions of the sulfuric acid react with the sodium ions of sodium hydroxide to produce sodium sulfate salt and water. Do remember that in an acid-base reaction, one of the products is always water. A double displacement reaction involves an exchange of ions between two compounds. The general form of a double displacement reaction is AB and CD undergo double displacement to form AD and CB. A classic example of a double displacement reaction is the reaction of magnesium oxide with calcium sulfide. In this reaction, magnesium and calcium ions interchange their places to form magnesium sulfide and calcium oxide. This reaction is known as a double displacement reaction because two compounds, magnesium sulfide and calcium oxide, are formed by the displacement of magnesium and calcium ions with each other. When the two reactants involved in a reaction are compounds, it is a double displacement. As you saw, in double displacement reactions, compounds exchange ions. However, in a combustion reaction, there is no exchange. In a combustion reaction, when all elements in a carbon compound combine with oxygen, they produce carbon dioxide and water. Thus, combustion reaction is the burning of a substance in the presence of oxygen, resulting in the release of energy, carbon dioxide, and water. For example, ethylene burns in the presence of oxygen to produce carbon dioxide, water, and heat. As a combustion reaction results in the release of heat energy, it is an exothermic reaction. Remember, a combustion reaction cannot occur without oxygen. There are some reactions that we see every day. Most of these reactions involve oxidation, reduction, or both. Oxidation reaction involves the addition of oxygen or the removal of hydrogen from a substance. This is a simple combination reaction. Two common examples of oxidation are rusting and rancidity. When an article made of iron is exposed to moist air for a long time, it turns reddish brown due to rusting. Here, iron is oxidized to form iron oxide. Chemically, rust is known as hydrated ferric oxide. Rusting of an iron article can be prevented by coating the surface with enamel, paint, or red lead oxide. Rancidity is the condition produced by the oxidation of fats and oils in food. It is marked by an unpleasant smell and taste. Two ways to protect food from rancidity are addition of an antioxidant. An antioxidant is a substance that prevents oxidation. Two common antioxidants used in food are butylated hydroxyaniso (BHA) and butylated hydroxytoluene (BHT). By packing food in nitrogen gas, nitrogen prevents oxidation of food. For example, rancidity in potato chips can be prevented by flushing the bags with nitrogen while packing. A reduction reaction involves addition of hydrogen or removal of oxygen from a substance. It is exactly the opposite of an oxidation reaction. For example, the formation of hydrogen sulfide involves a reduction reaction. In this reaction, when hydrogen is added to sulfur, sulfur gets reduced to hydrogen sulfide. Another example of a reduction reaction is photosynthesis. In plants, carbon dioxide and water are reduced to carbohydrates in the presence of light and the pigment chlorophyll. Oxidation and reduction reactions occurring together are known as redox reactions. In a redox reaction, a substance that gains oxygen is said to have been oxidized, and the one that loses oxygen is said to have been reduced. Let's use an example to explain redox reaction. Copper oxide on heating with hydrogen forms copper metal and water. In this reaction, the oxygen is removed from copper oxide. Here, copper oxide is reduced to copper. On the other hand, hydrogen is changed into water. That is, oxygen is added to hydrogen. So hydrogen is oxidized to water. Thus, we find that in this reaction, oxidation and reduction occur together. Therefore, it is redox reaction. All types of reactions result in either the release or the absorption of energy. Depending on energy considerations, chemical reactions can be classified into endothermic and exothermic. Endothermic reactions are those chemical reactions in which energy is absorbed. The energy absorbed is often in the form of heat energy or electrical energy. For example, sending electrical energy through a sodium chloride solution can cause it to break into its constituents, sodium and chlorine. On the other hand, exothermic reactions are the chemical reactions in which energy is released. For instance, when water is added slowly to a small quantity of quicklime or calcium oxide in a beaker, slaked lime or calcium hydroxide is formed and the beaker gets heated up. This is due to the evolution of heat during the reaction. Therefore, this is an exothermic reaction. All combustion reactions are exothermic reactions. For example, in the burning of coal, a large amount of heat is liberated. Therefore, it is an exothermic combustion reaction.